Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about molar relationships. We're going to talk about formula weights and how to calculate those, the difference between a formula weight and a molecular weight, how to calculate percent composition, what is a mole in Avogadro's number, as well as molar masses. So let's get into this video. So the first thing we're going to discuss is formula weight. In formula weight, you're first going to have to know how to name chemical compounds so that we can come up with the correct formula. From there, with a formula, you're going to look at the periodic table and you're going to look at the average atomic weight or mass at the bottom of each one of those squares for each individual element. So if we had an example like this one, calcium chloride, we've got CaCl2. So what we're going to do is we're going to consult the periodic table and look for calcium. We've got one calcium, and if we look here, we've got 40 AMU for the mass of one calcium atom. We also have 2 chlorine atoms in calcium chloride. So we're going to look up calcium's atomic weight, which is around 35.45, and we're going to multiply that by 2. To get the overall formula weight, what you're going to do is just sum all the different weights for each element. So we've got 40 plus about 71, which should total us 111 AMU. So this will be the formula weight of calcium chloride. The other term that we can have is called molecular weight. And the difference between a formula weight and a molecular weight is just what kind of compound you're looking at. But the way that you actually calculate this is the exact same way, so don't be confused. All you're going to do is look at the formula, look at the periodic table, determine how many atoms of the element you have, find its molar mass or its average atomic mass at the bottom of the square, multiply them, and then add them all up. So if we had this compound ethane, ethane only has nonmetals, so we would use the term molecular weight instead of formula weight. Formula weight is the more generic term that we would have, and we typically apply this to ionic compounds. So in this case, ethane is a molecule. We could say that we're going to calculate the molecular weight. So we've got 2 carbon atoms, each with a mass of about 12 AMU, so that's 24 AMU, plus 6 hydrogen atoms, each with a mass of 1 AMU. So the total molecular weight of ethane is 30 AMU. So just remember, ionic compounds are repeating units, yet we report these as empirical formulas, so you'd be calculating the formula weight. So the next thing that we can calculate once we understand how to calculate formula weights and molecular weights is the percent composition of an element within a compound. So here's the formula to do this. The percent composition of each element is going to be the number of atoms of that element times its atomic weight divided by the total molar mass or the molecular weight or formula weight. And you're just going to multiply that by 100. So if we're going back to our example of ethane and we want to find the percent carbon in ethane, what we would do is we've got 2 atoms of carbon. That has a mass of 12 AMU, so we're going to plug those 2 numbers on top of the fraction, and we're going to divide it by that 30 AMU we just calculated. And if we multiply by 100, we get about 79.88% carbon. We could do the same thing for hydrogen. You would just plug in how many hydrogen, 6 times 1 AMU divided by 30. Or if you only have 2 elements or whatever the last one is, you could just take 100% minus whatever you found. So if I take 100% and I subtract our 79.88% for carbon, since we got to add up to 100, the remaining would be due to hydrogen, which is approximately 20% hydrogen in this example. So let's start talking about the mole a little bit more in detail. The first guy who really started to define what a mole is was a scientist named Avogadro, and he came up with Avogadro's number. So we can't really work with single atoms or single molecules. It's not really useful to do that, as we can't really manipulate that or see that with our eyes. In the lab, we work with millions and millions of particles because we're at the macro scale, so we need to be able to fill graduated cylinders and beakers and such with different materials. So what he did is he defined a mole with a sample of carbon-12. So he had a pure isotope of carbon, all with a mass of 12 AMU in the nucleus, and he had a 12-gram sample of carbon-12. And he found that within this sample, there was 6.02 times 10 to the 23rd carbon atoms within this sample, and we define that as 1 mole. So a mole is just a conversion factor. We could have a mole of anything. We could have a mole of atoms. We could have a mole of molecules or particles. We could have a mole of pencils or elephants. It doesn't really matter. It's just a conversion factor. Just like a dozen is 12 and a pair is 2, 1 mole is 6.02 times 10 to the 23rd atoms per mole, or things per sample. Therefore, this is just a conversion factor. So we could convert from moles to number of particles, or number of particles back to the number of moles. So if we had a mole of water, and the formula of water is H2O, and we consult the periodic table for its formula weight or molecular weight, we could see that hydrogen has mass of 1, and water has 2 of those for a total of 2, plus we have an oxygen, which is 16 AMU. So we have a total of 18 AMU for one single water particle. If we had 1 mole, or 6.02 times 10 to the 23rd molecules of water, this would have a mass of 18 grams, which is going to be defined as our molar mass of water. So the molar mass is when we have 6.02 times 10 to the 23rd of that sample, and we're going to be defining this in grams, which is something we could actually measure on a balance in the lab. So that brings us to our last piece of the video, which is the idea of a molar mass. Molar mass is just the mass of 1 mole of a substance, and obviously every substance is going to have a different formula weight or molecular weight. So if we have something like diatomic oxygen, this is going to have 2 oxygen atoms for a total of 32 AMU. And if we had an Avogadro's number of these oxygen molecules, it would have a mass of 32 grams. So oxygen gas's molar mass is 32 gram per mole. We already talked about water. Water is 18 grams per mole. And we can also do this for ionic compounds like sodium chloride. Sodium chloride, we've got sodium, which is 23 AMU, plus chlorine, which is 35.45 AMU. So we get an approximate molar mass if we had 6.02 times 10 to the 23rd repeating units within our crystal. It would have a molar mass of 58.45 gram per mole. So our formula weight and our molecular weight are the same number as the molar mass. The only difference is the unit. If we're talking about formula weight and molecular weight, we're really talking about per 1 particle. And if we're talking about the molar mass, we're talking about an Avogadro's number of particles, or 6.02 times 10 to the 23rd of those particles. So the number's the same, but the unit is different and interchangeable. So then what we can do with our molar mass and Avogadro's number is use it as a conversion factor. We're just going to cram that between 2 parentheses with a division line in between, and we're going to set up our conversions, and we can flip them as well. So molar mass can be flipped depending on what direction you're going. If you have a mass sample from a balance in grams, you could divide by the molar mass and get the number of moles in that sample. If you have the number of moles, all you would do is flip the conversion factor, which would be the same as multiplying by the molar mass, and you could take your moles times molar mass and get the gram sample value. We could do the same thing with Avogadro's number. It's just a fraction conversion factor that we can flip one way or the other depending on what we want to do. If we have mole values, we can multiply by Avogadro's number, so multiply by 6.02 times 10 to the 23rd particles over 1 mole, and we can find the number of particles. Or if we have the number of particles or molecules, we can just divide by Avogadro's number, flipping the fraction, putting particles or molecule unit on the bottom, and we can just divide by that value and go from particles to moles. So there it is, you guys. There's the video on molar mass, percent composition, Avogadro's number, formula weights, and molecular weights. So if you found this video useful, smash the like button, send it to your favorite crab, send it to your favorite billionaire, and we'll see you in the next video.